What if I told you there's a dream that's been etched into the human spirit for generations? A dream so grand that it beckons us to reach into the vastness of space itself. Imagine standing on the surface of Mars, looking back at the tiny blue dot we call home, or walking beneath the towering rings of Saturn as they cast shimmering shadows on an alien landscape. Humanity's fascination with the cosmos is more than just an idle curiosity, it's an enduring quest, propelled by the desire to become a multi-planetary species. From the moment we first gazed up at the stars, we've been captivated by the possibility of what lies beyond. The allure of colonizing the solar system is about much more than just planting flags on distant worlds. It's about survival, exploration, and the ultimate adventure of understanding our place in the universe. While science fiction paints a vivid picture of thriving colonies on other planets, we must ask ourselves if this dream can ever be more than just fiction. Entering a new frontier brings with it untold challenges and mysteries. Yet, it's this vision of a future where humanity boldly inhabits the stars that continues to inspire our imagination and ignite the passion for discovery within us all. Stay with us as we explore the intricate layers of this celestial aspiration, unraveling the complexities and examining why, despite our technological advances, the dream of colonizing our solar system might remain just that, a dream. The technological hurdles we face in colonizing the solar system are profound and numerous. To traverse the vast expanses of space and settle on distant worlds, our current technology needs to make monumental leaps. Picture this: the closest planet, Mars, is still millions of miles away, a journey that could take several months with today's spacecraft. Our existing rockets, although marvels of engineering, simply cannot match the speeds required for efficient travel across the solar system. And even if we manage to get there, the challenge of building habitats that can withstand alien conditions is daunting. We need advancements in materials that can endure extreme temperatures and radiation levels unlike those on Earth. Furthermore, there's the matter of propulsion. The fuel technology we have today is not sustainable for long-term space travel. We need breakthroughs in propulsion technology that are yet to be realized, possibly nuclear or even electromagnetic, to make interplanetary travel viable. At present, our communication systems also pose a barrier. The further we travel from Earth, the more delayed our signals become, making real-time communication a distant possibility. Then there's the aspect of energy supply. Finding reliable, renewable energy sources in space to power our habitats and technology remains a significant challenge. Without these technological advancements, settling on other planets remains more of a visionary concept than a tangible reality. As we strive towards these goals, the gap between science fiction and practical application becomes ever clearer, underlining the vast technological journey we must undertake to even begin dreaming of colonization. The cost factor in space colonization is immense and underscores why this dream may remain beyond reach. Imagine the billions it takes just to launch a satellite or send a crew to a nearby space station. Now, multiply that by an astronomical figure to envision the expense of establishing sustainable colonies on other planets. Current estimates suggest that creating a self-sustaining colony on Mars alone could cost hundreds of billions, if not trillions of dollars. These figures dwarf the budgets of even the wealthiest nations. Our current financial capabilities are geared towards essential earthly needs and immediate scientific exploration, leaving little room for the extravagant expenses of space colonization. Even private companies, though ambitious and resourceful, grapple with the sheer economic scale required for such ventures. The truth is, the cost of transporting materials, building infrastructures, and ensuring the survival of colonists is staggeringly high. And then there's the need for continuous investment to maintain these colonies in inhospitable environments. If we compare our realistic financial resources with the monumental costs anticipated, It becomes clear that without a significant shift in economic priorities or the development of revolutionary, cost-effective technologies, the dream of colonizing the solar system remains financially out of reach. Survival in extreme environments presents a formidable challenge that significantly hampers the dream of solar system colonization. Picture the surface of Mars, where temperatures can plummet to 100 degrees Fahrenheit, or Venus, where heat can melt lead. These are conditions far removed from the relatively mild environment of Earth. The atmospheric pressure on Venus is 90 times that of Earth, while Mars has a thin atmosphere composed mainly of carbon dioxide, offering little protection from cosmic and solar radiation. This means we would need to develop habitats that can shield humans from such extremes, providing stable temperatures, adequate pressure, and breathable air. But it's not just about the temperature and atmosphere. Dust storms on Mars can last for months, potentially compromising our equipment and habitats. On the gas giants like Jupiter and Saturn, the intense gravity and lack of a solid surface make these locations unsuitable for traditional settlement. Building sustainable habitats also means ensuring a continuous supply of essential resources like water and food, which are not naturally available on most celestial bodies. This would require innovative solutions such as closed-loop life support systems and advanced agricultural techniques capable of functioning in low-light and low-gravity environments. Another issue is the psychological strain of living in confined spaces, isolated from Earth for extended periods. Creating an environment that supports mental health is just as critical as physical survival. The complexity of adapting to these extreme conditions underscores the enormous engineering and biological hurdles we must overcome. Despite our best efforts and ingenuity, these challenges continue to highlight the harsh realities of living beyond our planet, making the dream of colonizing the solar system appear elusive and distant. The limitations of our current spacecraft technology are a huge obstacle in the dream of space colonization. Let's start with speed. Imagine traveling to Mars. Even the fastest spacecraft at our disposal would take months to reach this neighboring planet. We're bound by the limitations of chemical propulsion, which, despite advancements, remains relatively slow. Speed is crucial when considering the vast distances in our solar system, and our current capabilities mean long journeys fraught with risks. Next is fuel capacity. Our spacecraft require significant amounts of fuel to launch, maintain trajectory, and land safely. This limits the size and weight of what we can send into space. Once the fuel runs out, a spacecraft is left drifting, unable to change course or speed. The prospect of carrying enough fuel to sustain long interplanetary voyages and return trips is not feasible with today's technology. This is why finding alternative propulsion methods, perhaps through nuclear or ion propulsion, is essential, yet these solutions are still largely in the experimental phase. Durability is another concern. Spacecraft must endure harsh conditions, from intense radiation to micrometeoroid impacts and extreme temperatures. Yet our crafts are designed primarily for short-term missions, making the idea of long-term planetary travel risky. The wear and tear during extended missions can lead to mechanical failures, posing severe threats to crew safety. Lastly, consider the pace of innovation in spacecraft technology, which has been more incremental than exponential. While we've seen groundbreaking achievements like landing a rover on Mars or sending probes to the outer reaches of our solar system, these have not translated into a revolution in colonization capabilities. The technological gap remains wide, and until we significantly innovate these areas, our spacecraft will continue to constrain our extraterrestrial ambitions. Hence, the dream of colonizing planets may remain a distant fantasy, tied down by the limitations of our current spacecraft technology. The risks to human health in space are vast and complex. Imagine spending months in a tiny spacecraft where the absence of gravity causes muscles to weaken and bones to lose density. This condition, known as muscle atrophy, is a serious concern for astronauts on long missions. Without the constant pull of Earth's gravity, our bodies undergo changes that can impair mobility and strength over time. But it doesn't stop there. Space radiation is another invisible threat. Unlike on Earth, where our atmosphere provides protection, space offers no such shield. High-energy particles from the sun and cosmic rays can penetrate our spacecraft, increasing the risk of cancer and other health complications. Ensuring adequate protection against this radiation is critical, yet remains a significant challenge. Then there's the psychological impact of isolation. Long-duration space missions mean being confined with a small group of people, cut off from loved ones and the familiar comforts of Earth. This isolation can lead to stress, anxiety, and depression, affecting mental well-being and performance. The absence of natural light and the monotony of daily routines intensify these feelings, making mental health support as crucial as physical health care. Additionally, the disruption of circadian rhythms due to the lack of a day-night cycle can impact sleep and cognitive functions. To tackle these health risks, we need comprehensive solutions that include physical exercises to mitigate muscle loss, advanced shielding technologies to protect against radiation, and robust support systems to maintain mental health. The reality is, while we can send humans to space for short periods, the health risks associated with prolonged exposure present formidable obstacles. Overcoming these challenges is essential to turn the dream of space colonization into a reality. Until then, the continuous threat to human health will remain a key factor in why colonizing the solar system is still beyond reach. The concept of terraforming, transforming the barren landscapes of other planets into habitable environments similar to Earth, is a captivating idea. Imagine turning the red, dusty plains of Mars into lush green fields or altering Venus's acidic atmosphere to support human life. Yet, as intriguing as it sounds, terraforming remains firmly in the realm of theory. The challenges we face in making this a reality are daunting. To begin with, altering a planet's atmosphere on a scale necessary for human settlement isn't just a matter of adding oxygen or reducing carbon dioxide. It requires massive technological interventions and immense energy resources, far exceeding our current capabilities. Scientists propose methods like melting polar ice caps on Mars to release carbon dioxide and thicken the atmosphere, but this process would take centuries to achieve meaningful results. Another significant hurdle is the ethical and ecological implications. What right do we have to modify entire ecosystems, potentially wiping out any existing microbial life forms? Moreover, the logistics of managing such changes on a planetary scale are staggering. Terraforming efforts would need to be precisely controlled to avoid creating unstable environments that could harm rather than help potential settlers. Then there's the issue of timescales. Terraforming a planet isn't a project that can be completed in decades. We're talking about processes that might span thousands of years, demanding sustained commitment across generations, something humanity has never attempted on such a scale. Even the basic assumption that a planet can be made Earth-like is still under scrutiny, with many scientific unknowns adding layers of uncertainty. The reality is that while terraforming captures our imagination, it remains speculative with many unresolved scientific and ethical questions. This theoretical nature of terraforming showcases yet another reason why the dream of colonizing the solar system remains an elusive vision rather than an imminent reality. Resource scarcity is a critical challenge when it comes to the dream of colonizing the solar system. Imagine trying to survive on a planet where essential resources like water, oxygen, and food are either incredibly scarce or entirely absent. Water, the most crucial resource for life, is not readily available on most planets. While we've found evidence of frozen water on Mars and the Moon, extracting it is a complex and energy-intensive process. Without a reliable water source, sustaining human colonies would be nearly impossible. Then there's oxygen, another vital component for human survival. Our Earth provides it freely, but other planets lack breathable atmospheres. This means we would need advanced life support systems capable of generating oxygen from available resources, like splitting water into hydrogen and oxygen, or using plants for photosynthesis. But these systems themselves require maintenance and resources to function, adding another layer of complexity. Food production presents yet another hurdle. The idea of transporting food supplies from Earth to sustain a colony on another planet is both impractical and unsustainable in the long term. Growing food in space would require innovative agricultural techniques such as hydroponics or aeroponics, which can function in low-gravity environments. These methods are still under development and would need to be significantly scaled up to meet the needs of a colony. Additionally, the logistics of transporting resources from Earth to other planets are daunting. Current rockets have limited cargo capacity, and the cost of sending materials into space is astronomical. Each mission would need meticulous planning to ensure all necessary supplies are available and that nothing essential is left behind. Even with potential advances in technology, the sheer volume of resources required to support human life on another planet poses a significant challenge. Addressing resource scarcity is crucial because it directly impacts the viability of long-term space habitation. Until we can solve these logistical issues and develop sustainable ways to produce and recycle resources in space, the dream of solar system colonization will likely remain out of reach. Ethical and legal concerns are pivotal when it comes to the idea of colonizing other celestial bodies. Imagine staking a claim on a piece of land on Mars or mining an asteroid for precious metals. These actions raise profound questions about ownership and stewardship in space. Unlike Earth, where national boundaries and property laws guide ownership, space lacks a clear legal framework for such claims. The Outer Space Treaty of 1967, which most nations have signed, prohibits any country from claiming sovereignty over celestial bodies. This means that while countries can explore and use outer space, they cannot own any part of it. But the treaty, drafted more than 50 years ago, did not anticipate the rise of private companies in space exploration. This creates a legal gray area where companies might seek to exploit resources without clear international regulations to guide them. Furthermore, there's the question of stewardship. As we explore other planets, we must consider our responsibility to preserve their natural state. Introducing Earth-based life forms could potentially disrupt alien ecosystems, even if they are microbial. The ethical dilemma of whether we have the right to alter other worlds to suit our needs is significant. We must also consider the impact on potential local life forms and the long-term effects of our presence on these celestial bodies. These complexities highlight the need for updated international space laws that address the realities of modern space exploration. Without a robust legal and ethical framework, the prospect of colonizing the solar system not only challenges our technological capabilities, but also raises profound questions about our role as stewards of the cosmos. It reminds us that the dream of space colonization involves more than conquering new frontiers. It requires us to navigate these moral and legal challenges with great care and responsibility. Political and international dynamics play a crucial role in shaping the future of space colonization, often introducing complexities that can impede progress. Imagine attempting to establish a colony on another planet, only to find that political disagreements on Earth spill over into space. Global politics, with its intricate web of alliances, rivalries, and treaties, can significantly influence space exploration efforts. Consider the competitive nature of nations vying for dominance in technology and space capabilities. This competition can lead to a lack of cooperation, where countries prioritize national interests over collective progress. For instance, instead of pooling resources and knowledge, nations might focus on solo missions, leading to redundancy and inefficiency. International treaties, such as the aforementioned Outer Space Treaty, aim to keep space exploration peaceful and benefit all humanity. However, the absence of a clear framework to address the involvement of private companies and new spacefaring nations creates ambiguity, often leaving loopholes that can hinder collaborative efforts. Moreover, the geopolitical implications of space colonization are vast, as the potential for resource extraction from celestial bodies could shift economic power dynamics on Earth, prompting nations to protect their interests aggressively. Political tensions and mistrust between countries can further complicate efforts to establish international space governance. To navigate these political and international challenges, there must be a renewed commitment to fostering global cooperation and establishing comprehensive regulations that address the evolving landscape of space exploration. Without a unified approach and adherence to mutually agreed upon rules, the dream of colonizing the solar system could become mired in earthly political conflicts, stalling the progress needed to turn this vision into a reality. The sustainability problem casts a significant shadow over the dream of colonizing the solar system. Building self-sustaining colonies is a monumental challenge, primarily due to our current technological constraints and resource limitations. Imagine a colony on Mars that needs to function independently from Earth, producing its own food, water, and oxygen, all while managing waste and energy consumption efficiently. To achieve this, we would require closed-loop life support systems that can recycle everything from air and water to nutrients, similar to Earth's natural ecosystems. Yet, developing such systems remains complex. Our technology is not yet advanced enough to achieve this level of sustainability, especially in harsh extraterrestrial environments. Furthermore, the energy dilemma complicates matters. Solar panels, though effective on Earth, provide limited energy on distant planets due to varying distances from the Sun and frequent dust storms, like those on Mars, obscuring sunlight. We need innovative solutions for reliable energy generation, perhaps through nuclear reactors or fusion power, yet these technologies also come with their hurdles. Moreover, the logistics of transporting or manufacturing the necessary components for these life support systems pose another bottleneck. With the current limitations of our spacecraft, sending the vast amount of equipment and materials needed is both economically and technically challenging. This means that any colony must be able to extract and utilize local resources efficiently, which requires advances in mining and manufacturing technologies that we have yet to realize. Additionally, the psychological aspect of isolation and confinement in an artificial environment can affect settlers' mental wellness, influencing their ability to maintain a self-sustaining ecosystem. All these challenges highlight why establishing self-sustaining colonies is still far from reality. Without groundbreaking advancements in technology and sustainable resource management, the hope of creating independent colonies in our solar system remains an elusive goal, perpetuating the notion that colonizing the cosmos might remain a distant dream. The timescale issue is a crucial factor that underscores the daunting reality of space colonization. Imagine embarking on a journey where milestones are not reached in weeks, months, or even years, but in centuries. The effort to establish human habitats on other planets requires patience on a scale that humankind has rarely exhibited. Take, for instance, the notion of sending humans to Mars. Even with the most optimistic projections, such missions could take decades just to plan and execute. Once there, building a viable colony would necessitate years of continuous effort with no guarantee of success. This is not a sprint but a marathon through the unknown. The immense distances involved mean that transporting materials and personnel will be a slow, tedious process hampered by current spacecraft limitations. Moreover, technological breakthroughs such as developing self-sufficient life support systems and energy solutions are needed, and these do not happen overnight. Even the terraforming of a planet, as we discussed earlier, could take thousands of years, requiring multi-generational commitment without immediate results. In a world accustomed to quick fixes and rapid technological advancement, the prospect of waiting centuries presents a significant psychological and practical barrier. It demands a profound shift in how we view progress and success, moving beyond individual accomplishment to a legacy that may only be realized by distant descendants. To approach such vast timescales requires a collective vision and sustained dedication that transcends individual and national interests. Without cultivating this patience and long-term perspective, the dream of colonizing worlds beyond our own remains just that, a distant vision in the face of monumental time challenges. The role of private companies in advancing the dream of colonizing the solar system is undeniably significant, yet it comes with its own set of limitations. Over the past few decades, we've witnessed private companies emerge as major players in space exploration, driven by innovation and ambition. Companies like SpaceX and Blue Origin have pushed boundaries, developing reusable rockets and reducing the cost of space travel substantially. Their contributions can't be overstated. These companies have injected a competitive spirit into the industry, spurring technological advancements that might have taken longer in the traditional government-led programs. The agility and flexibility of private enterprises allow them to take risks and innovate at a pace often unmatched by larger governmental agencies. Yet, despite these impressive achievements, there are inherent limitations. Private companies primarily operate on a profit-driven model, meaning their long-term commitment to space colonization hinges on economic viability. Unlike governmental agencies that can pursue space exploration for national interest and scientific advancement, private companies must justify their ventures with tangible economic returns. This focus on profitability can narrow their objectives, potentially sidelining broader scientific goals. Moreover, the resources available to these companies, although substantial, pale in comparison to the budgets and infrastructure of governmental agencies like NASA or ESA, which have decades of expertise and international collaboration at their disposal. When we compare the two, governmental agencies have the advantage of comprehensive regulatory frameworks and international treaties that guide exploration and ensure safety standards. These ensure a unified approach to space exploration, something that private companies must navigate carefully. Collaboration between public and private sectors may offer the best path forward, combining innovation with experience and stability. However, without this synergy, private companies alone cannot shoulder the immense challenge of colonizing the solar system. They act as dynamic catalysts, but the dream of establishing human outposts beyond Earth requires a concerted effort that transcends individual enterprises, necessitating a partnership that blends the strengths of both private ingenuity and public stewardship. The unknowns of space present a myriad of challenges that further complicate the dream of colonizing the solar system. Imagine venturing into a realm where not all variables are known, and unpredictable cosmic events could alter the course of well-laid plans. Space is a vast, largely unexplored frontier, and this mystery brings both excitement and significant risk. One of the primary unknowns is the occurrence of cosmic events such as solar flares, which can unleash intense radiation that poses a threat to both humans and technology in space. These flares can disrupt communication and navigation systems, putting missions at risk. There's also the uncertainty of asteroid impacts, which, despite our advances in detection technology, cannot always be predicted with precision. The potential for these sudden, catastrophic events adds a layer of complexity to colonization plans. In addition to natural phenomena, there are technical failures that are difficult to foresee. Space missions rely heavily on advanced technology, yet even the most meticulously designed systems are not immune to breakages or glitches. As we push the boundaries of our technological capabilities, the likelihood of encountering unforeseen technical issues increases. For instance, malfunctions in life support systems or propulsion engines could have dire consequences for those on board. This unpredictability demands robust contingency planning and an ability to adapt quickly to unexpected situations, both of which require substantial resources and expertise. Furthermore, our understanding of the long-term effects of space travel on human physiology remains incomplete. Despite rigorous research, the impact of prolonged exposure to microgravity and radiation is still not entirely understood, and unknown health implications could emerge as missions extend over months or even years. These unknowns serve as a stark reminder of the peril and unpredictability that comes with exploring the cosmos. They highlight the critical need for resilience, innovation, and international cooperation to address these uncertainties. Without a comprehensive understanding and preparation for these unknown challenges, the vision of establishing human colonies in space will continue to face significant obstacles, reinforcing the notion that colonizing the solar system may remain just out of reach. Life support systems are the unsung heroes of any space mission, and they become even more critical when we talk about long-term human habitation in space. Imagine living in an environment where every breath you take and every sip of water comes from a complex system designed to sustain life far from Earth. These systems are responsible for providing essential resources like oxygen and water, as well as managing waste and keeping the right balance of air pressure and temperature. On Earth, we often take these elements for granted because they are naturally abundant. But in space, they are precious commodities that require intricate engineering to produce and maintain. One key function of life support systems is oxygen generation, which is typically achieved through methods like electrolysis, where water molecules are split into hydrogen and oxygen. But this process, along with others, requires a significant amount of power and resources, and any failure can be life-threatening. Similarly, water recovery systems aim to recycle every drop of water used on board from sweat to urine to ensure sustainability. Yet, while these technologies are advancing, they are not foolproof and have limitations in efficiency and reliability. Another challenge is maintaining a stable atmosphere and comfortable temperature within spacecraft or habitats, especially when external conditions are harsh and fluctuating. Waste management also poses a significant hurdle. Without Earth's natural recycling systems, managing waste in a closed environment becomes a complex task, requiring innovative solutions to ensure the safety and health of the crew. Moreover, the need for regular maintenance and spare parts adds another layer of complexity, especially when missions are far from Earth support. These limitations underscore the immense challenge of creating life support systems capable of sustaining human life for extended periods in space. While we have made remarkable progress in this field, the current systems are not yet equipped to handle the scale and duration required for solar system colonization. Until we achieve breakthroughs in life support technology that allow for greater autonomy and resilience, the prospect of establishing long-term human colonies in space continues to face significant barriers. The psychological factor plays a crucial role in the viability of long-term space colonization. Imagine living in a confined space, isolated from your home planet, with the same limited group of people for years on end. The sense of separation from Earth, the vast emptiness surrounding you, the absence of familiar sights and sounds, all contribute to a profound psychological strain. The lack of natural stimuli and the monotony of daily life can lead to feelings of claustrophobia, anxiety, and depression. In addition, the pressure of living in a high-stakes environment where survival depends on complex systems functioning perfectly can heighten stress levels. This psychological burden is compounded by the knowledge that any help from Earth would be months away, fostering a sense of vulnerability. Maintaining mental well-being in such conditions requires robust psychological support systems to help manage these stressors. Tools such as virtual reality environments that simulate Earth-like settings, comprehensive communication systems to maintain connections with loved ones, and structured routines that allow for recreation and personal development are essential. Moreover, the crew's selection process needs to emphasize psychological resilience and compatibility to ensure a harmonious living environment. The reality is that while we focus on technological advancements, mental health remains a fundamental aspect of space colonization that cannot be overlooked. Addressing these psychological challenges is vital as they directly impact performance, teamwork, and overall mission success. Until we develop effective strategies to support mental health in these isolated and confined settings, the dream of colonizing distant worlds will continue to face significant hurdles. Contingency planning is the backbone of ensuring safety for any space settlers, acting as a safeguard against the unpredictable nature of space. Imagine being on a distant planet where the success of your mission rests on the ability to swiftly and effectively respond to emergencies. This requires a vast array of contingency plans that address potential crises. In an environment as hostile as space, where the margin for error is razor thin, every aspect of life and operation needs a backup plan. From system malfunctions and supply shortages to medical emergencies and unplanned environmental changes, the scope of potential issues is immense. For example, should a life support system fail, there must be immediate protocols to maintain breathable air and water supply. Similarly, in the event of a power outage, backup energy sources should be readily available to ensure critical systems remain operational. Medical emergencies pose another set of challenges, requiring advanced medical equipment and trained personnel to handle anything from minor injuries to severe health conditions without the immediate support of Earth-based facilities. Beyond technological and medical readiness, the psychological aspect of emergency planning cannot be ignored. Settlers need to be mentally prepared to handle high-stress situations, and this involves regular training and simulations that reinforce calm and effective crisis management. Collaborative problem solving and clear communication are essential skills in these scenarios, and crews must be equipped to work seamlessly under pressure. Moreover, contingency planning extends to communication systems. With the vast distances involved, maintaining reliable contact with Earth during an emergency is crucial, necessitating redundant communication pathways that can function independently if primary systems fail. Ultimately, these contingency plans are about building resilience into the fabric of space settlements, ensuring that when faced with the unexpected, settlers are equipped to adapt and survive. Without these extensive preparations, the risks grow exponentially, underscoring yet another layer of complexity in the dream of establishing human colonies beyond Earth, a vision that remains challenging due to the intricate demands of planning for every conceivable emergency. Space station limitations highlight the considerable gaps we must bridge to pave the way for true space settlement. Imagine the International Space Station, a marvel of human engineering, yet it remains a temporary residence designed for short-term scientific missions rather than permanent habitation. One primary limitation is size. Current space stations offer limited living and working space, constraining the number of occupants and the duration of their stay. Unlike a colony, a space station cannot support a large, self-sustaining community. Then there's the matter of resources. Space stations rely heavily on regular resupply from Earth, including food, water, and essential equipment. This dependency underscores the difficulty in achieving the level of autonomy required for off-world colonies. Moreover, life support systems aboard stations are sophisticated yet not fully capable of supporting long-term habitation without external aid. Another issue is the limited gravity simulation. The microgravity environment affects human health over time, causing muscle atrophy and bone density loss, issues that would be detrimental over extended periods. Developing gravity simulation technologies is crucial for maintaining long-term human health. Energy generation poses another hurdle. space stations primarily rely on solar panels, which have limitations in energy output and efficiency, especially as we consider more distant and less sunny locales. Furthermore, the construction and maintenance logistics of larger, more robust stations face engineering challenges that are yet to be overcome. The complexity of assembling and maintaining these structures in space requires advanced robotics and automated systems that are still in development. These barriers illustrate why current space stations serve as enlightening precursors but fall short of enabling true space settlement. Addressing these limitations with innovative solutions is imperative if we hope to advance from temporary habitats to enduring colonies in space. Until then, the vision of colonizing the solar system remains a formidable challenge. Cultural shifts required for space colonization are profound, demanding a re-evaluation of our societal priorities. Imagine a world where the collective focus isn't solely on national boundaries or earthly concerns, but on a unified quest to explore and inhabit new worlds. This shift involves embracing a global mindset that sees humanity as one interconnected species, bound together by the shared goal of cosmic exploration. To prioritize space colonization, we must cultivate a culture that values long-term scientific endeavors and exploration over immediate gratification. This might mean reallocating resources and public support from traditional industries to those that advance space technology and research. It also requires fostering curiosity and education in science and technology from a young age, encouraging future generations to pursue careers that will contribute to our off-world ambitions. Furthermore, societal values must evolve to recognize the importance of collaboration over competition. Imagine nations investing in joint missions instead of isolated efforts, pooling their knowledge and resources to overcome the monumental challenges of space colonization. To achieve this, political leaders and institutions must champion policies that support international cooperation in space as an essential component of national and global progress. Additionally, we must consider the narrative surrounding space exploration. By framing it as a continuation of humanity's innate drive to explore the unknown, we can inspire public passion and commitment. This narrative shift helps the public see space colonization as not just a scientific endeavor, but a cultural and existential journey. Embracing these shifts requires patience and effort, but they are crucial if we aim to turn the dream of exploring and inhabiting the solar system into reality. Only then can we hope to transcend our terrestrial limitations, uniting under a shared vision of cosmic discovery. The energy puzzle presents a significant hurdle in the quest for colonizing the solar system. Imagine trying to power an entire colony on Mars, where sunshine is less abundant and dust storms can obscure the sun for weeks, drastically reducing the efficiency of solar panels. On Earth, we have a variety of energy sources to rely on, but in space, the options are limited and none are straightforward. Solar power, while effective for certain applications, faces challenges with reliability and output consistency in the variable environments of other planets and moons. Additionally, the further we travel from the Sun, the less effective solar power becomes. On the other hand, nuclear power, which could provide a steady and robust energy supply, raises concerns about safety and radioactive waste management in a delicate extraterrestrial ecosystem. Even on Mars, where solar power might be most feasible, the sheer scale needed to support a thriving colony presents logistic and technological difficulties. To create a sustainable energy infrastructure, we would need to develop compact, efficient power sources capable of operating in harsh conditions with minimal maintenance. Then there's the challenge of energy storage. Current battery technology, though constantly improving, struggles to store energy for extended periods without loss, limiting its practicality for long-term space missions. Innovative solutions like advanced fuel cells or enhanced battery systems need to be developed to bridge this gap. Furthermore, the concept of beaming energy, transmitting power wirelessly over long distances, is also under consideration, but this idea is still in its infancy and faces numerous technical hurdles. Addressing these energy challenges is crucial because a reliable, sustainable energy supply is foundational to any space colony's success. Without breakthroughs in energy generation and storage technology, the dream of colonizing the solar system remains fraught with uncertainty, serving as a stark reminder of the complex tapestry of challenges we must unravel to one day call the cosmos our home. Exploring the potential environmental impact of colonization efforts on celestial bodies and the surrounding space environment, we face a sobering reality that echoes the challenges we encounter on Earth. Imagine deploying human settlements across the solar system, barren landscapes transformed into bustling colonies. As enticing as this vision is, it brings with it a host of environmental concerns. On celestial bodies, the introduction of human presence and technology could lead to contamination of pristine environments, disrupting any existing ecosystems, whether microbial or purely geological. The very act of landing spacecraft, constructing habitats, and extracting resources for survival poses risks to the integrity of these alien landscapes. Our exploration-driven activities could irrevocably alter the natural state of these bodies, leaving behind pollution and waste that could linger for millennia. Beyond the celestial terrains, the broader space environment faces its own set of challenges. Each mission contributes additional debris to the ever-growing clutter surrounding our planet. The potential for collisions increases, which can have a cascading effect, creating more hazardous debris that threatens other spacecraft. This not only poses risks to future missions, but also to the delicate balance of the space environment itself. Moreover, the extraction of resources from celestial bodies for colonization could deplete their natural reserves, mirroring the resource exploitation issues we face on Earth. The question then arises, do we have the right to harness these resources, and at what cost? Without stringent environmental guidelines and practices, we risk exporting our ecological footprints into the cosmos. As we contemplate colonizing the solar system, it's vital to consider these environmental challenges with the utmost seriousness. Balancing human ambition with the ethical responsibility to preserve the sanctity of extraterrestrial environments is essential. Only by adopting sustainable and respectful exploration practices can we hope to tread lightly among the stars, ensuring that the dream of solar system colonization does not lead to ecological harm beyond our planet. The distance dilemma presents a formidable challenge in the pursuit of colonizing the solar system. Imagine the vastness of space, where even our closest planetary neighbor, Mars, is millions of miles away. This immense separation between celestial bodies introduces significant complexity in both communication and material transport. For communication, the vast distances result in substantial delays. A signal sent from Earth to Mars can take several minutes to arrive, depending on the planet's relative positions. This means that real-time communication, something we take for granted on Earth, becomes a daunting task. Delays complicate mission control operations, making immediate responses to emergencies impossible. The further we venture into the solar system, the longer these communication lags become, challenging the coordination of missions and the transmission of critical data. In terms of material transport, the distances involved are equally problematic. Sending supplies, equipment, or personnel across millions of miles is an arduous and costly endeavor. The fuel requirements alone for such journeys are immense, as current technology restricts our ability to transport large payloads efficiently. The longer the distance, the more energy and resources are needed to bridge the gap, increasing both the expense and risk of transport missions. Additionally, the isolation caused by these distances dictates the need for self-sufficiency within any space habitat. Colonies must be able to produce their own food, water, and materials, since resupply missions would be intermittent and limited by the long travel times. This requirement for autonomy adds another layer of complexity to the already challenging task of establishing human settlements on distant worlds. The reality is that until we break through the technological barriers posed by these vast distances, the vision of a connected and thriving solar system remains elusive. The distance dilemma stands as a stark reminder of the daunting logistical challenges we must overcome to realize the dream of becoming a multi-planetary species. The role of AI and robotics in aiding our ambitious pursuit of space colonization is both promising and challenging. Imagine a future where intelligent robots prepare the unwelcoming terrains of other planets, building shelters, extracting resources, and even assisting in farming, all before human settlers arrive. AI and robotics promise to be our stalwart allies, capable of performing tasks that would otherwise be too dangerous or labor-intensive for humans. Advanced algorithms can analyze vast amounts of data to make efficient decisions on the fly, while robotic explorers can endure the harsh conditions of space far longer than any human. Automation through AI has the potential to significantly reduce the cost and risk of operations by handling mundane yet crucial tasks, allowing humans to focus on more strategic aspects of colonization. Yet, this dream is not without its limitations. Current AI technologies, although remarkable, are not yet sophisticated enough to completely replace human judgment or creativity in unpredictable situations. Machine learning systems require vast amounts of data to function effectively, and the unique conditions of space present unfamiliar variables that could confound even the most advanced AI. Furthermore, robotics technology, while evolving rapidly, still faces challenges like mobility on uneven terrain, power supply limitations, and maintaining operation over extended periods without the need for human intervention. The need for reliable and autonomous systems is paramount, as reliance on remote control from Earth introduces delays and communication challenges. Ensuring these machines can independently handle unexpected obstacles and perform repairs is a significant technological hurdle yet to be overcome. Additionally, the ethical considerations of relying heavily on AI and robotics cannot be dismissed. As we entrust machines with more responsibilities, questions about accountability and the potential displacement of human labor in space missions arise. Thus, while AI and robotics hold great promise in aiding space colonization, significant advances in their capabilities and ethical frameworks are necessary. Only by addressing these technological and moral complexities can we harness the full potential of AI and robotics, turning them into indispensable partners in our quest to explore the cosmos. Throughout the annals of space exploration, the path to the stars has been paved with both triumphs and setbacks, underscoring the trial and error nature inherent in this grand endeavor. Imagine the early days of space exploration, where each mission was a bold leap into the unknown, fraught with risks and uncertainties. The legacy of missteps spans these formative years, reminding us of the formidable challenges we face in our quest to colonize the solar system. Consider the Apollo 1 tragedy in the 1960s, where a cabin fire during a pre-launch test claimed the lives of 3 astronauts. This heartbreaking incident highlighted the crucial importance of safety and rigorous testing, which became foundational to future missions. Then there's the Challenger disaster in 1986, a stark reminder of the vulnerabilities in human spaceflight. These tragedies taught us that even with meticulous planning and engineering, unforeseen issues can arise, emphasizing the need for constant vigilance and innovation. But setbacks are not limited to crewed missions. Numerous robotic endeavors, such as the Mars Climate Orbiter, which was lost due to a simple conversion error between metric and imperial units, teach us about the intricacies and precision required in space navigation and operations. Failures like these underscore the complexities of managing space missions and the delicate balance between human oversight and technological reliance. The Beagle 2 lander that disappeared during its descent onto Mars serves as a reminder of the harsh and unforgiving nature of space environments. Each failure, while a setback, carries invaluable lessons, steering future endeavors with greater caution and understanding. Yet, it is this iterative process, learning from failures, adapting and improving, that forms the crux of space exploration. These missteps, although painful, become stepping stones toward success, driving the relentless pursuit of discovery. The reality is that space exploration is an ongoing journey of learning and adaptation, where every failure refines our methods and strengthens our resolve. This legacy of trial and error continues to shape our efforts, highlighting the immense challenges that must be overcome to transform the dream of solar system colonization into a reality. In summary, the compelling vision of colonizing the solar system faces a myriad of overwhelming challenges that firmly anchor it as a distant dream rather than an imminent reality. Our journey has taken us through the formidable technological gaps, astronomical costs, and survival challenges posed by extreme environments. We've examined the limitations of spacecraft technology and the profound health risks associated with space travel. Terraforming remains a theoretical endeavor fraught with scientific and ethical dilemmas, while resource scarcity and the logistics of transport present formidable barriers. Ethical, legal, and political considerations further complicate the tapestry of space colonization, while the immense timescales demand a patience humanity has rarely exhibited. While private companies push the boundaries, they too are constrained by economic viability and resource limitations. The vast unknowns of space, from cosmic events to unforeseen technical failures, add further complexity to an already challenging pursuit. Life support systems, psychological factors, and contingency planning underscore the intricate web of needs to ensure safety and well-being in space. Current space stations, cultural shifts, energy puzzles, and environmental concerns all highlight the distance we must travel to achieve this celestial dream. The distance dilemma, limitations of AI and robotics, and the legacy of past missteps serve as reminders of the significant hurdles we face. As we look toward the stars, we invite you to reflect on humanity's course in space exploration. It's a journey not just defined by technological advancement, but by the ethical and communal spirit we choose to embrace. How we address these formidable challenges will dictate our future among the stars. We encourage you to ponder these questions and join the conversation around humanity's aspirations and responsibilities in the vastness of the cosmos. If you found this exploration insightful, please subscribe, like, and hit the notification bell to stay updated on our journey through the frontiers of technology and space. Thank you for joining us in contemplating the possibilities and realities of our cosmic future.